Hey everyone, and welcome back to AI Paper Podcasts. Today we are diving deep into a paper all about making large language models think leaner.
Think leaner.
Yeah, think leaner. It's called LightThinker, Thinking Step-by-Step Compression from Zhejiang University and the Ant Group. And it's all about compressing an LLM's thoughts on the fly, to make them more efficient.
Ah, I see. So like slimming down the thought process.
Exactly. Now, before we get into the nitty-gritty, let's set the stage a bit. We're talking about these large language models, especially the ones that excel at slow thinking, those step-by-step reasoning processes.
Right, like chain of thought or the O1-like mode.
Exactly. But the problem is, even if the final answer is short and sweet, these models generate a ton of text along the way as they're thinking things through.
It's like they're writing down every single thought, no matter how small or irrelevant. Like a brainstorming session that just goes on and on.
Yeah, it's like having a super smart detective, but they need to document every single clue, every hunch, every dead end.
And all that extra stuff can lead to some serious bottlenecks.
Bottlenecks? What kind of bottlenecks?
Well, first, you've got memory overhead. All those tokens need to be stored somewhere, and that takes up a lot of space.
Yeah, it's like trying to cram a whole library into a tiny shoebox.
Exactly. And then there's the computational cost. Processing all that text slows the model down significantly.
So it's not just about storage space, it's about processing power too. The more data the model has to churn through, the longer it takes to get to the answer. Makes sense. So just how bad does this memory problem actually get?
Well, let's take the Qwen32B model, for example. The KV cache, which is where the model's attention information is stored, can actually become as large as the model itself.
Whoa. Hold on. So you're saying that the memory needed to keep track of all the model's thoughts can be as big as the model itself?
Yep. Especially when you're dealing with a context length of 10,000 tokens.
10,000 tokens. That's a lot of text. No wonder efficiency is a major concern. And then on top of that, you have the computational cost. Does that scale in a similar way?
It actually gets even worse. The complexity of the attention mechanism grows quadratically with the context length.
Quadratically?
Right.
So longer those thought chains get, the slower the model becomes at an accelerating rate.
Exactly. It's a real challenge. So of course people have tried to tackle this problem.
Yeah, I was going to ask, what are some of the existing solutions out there?
Well, there are two main approaches. The first is to try and get the LLM to generate fewer tokens in the first place.
So make it a more concise thinker from the get-go.
Right. And that can be done through prompt engineering, carefully crafting the instructions you give the model, or by training it specifically to be more concise.
Okay, so streamlining the thought process itself. What's the other approach?
The other approach is to prune the less important data during inference. It's kind of like tidying up as you go along, getting rid of the clutter you don't need.
I like that analogy.
Right.
Makes sense. But I'm guessing both these approaches have their own drawbacks.
Of course. Prompt engineering can be tricky, and it's not always clear how to get the model to be concise without sacrificing accuracy.
Right. You don't want to lose the brilliance in the quest for efficiency. And what about pruning?
Pruning can be effective in reducing memory usage, but it adds latency because the model has to constantly decide what to keep and what to discard.
So it's like a trade-off between memory efficiency and processing speed.
Yeah.
It sounds like a tough nut to crack. So how does LightThinker approach this problem?
Well, the researchers behind LightThinker had a really interesting insight. They looked at how humans reason and realized that we don't write down every single thought. We summarize, we abstract, we focus on the key points.
Right, we don't keep a verbatim transcript of our every thought process.
Exactly. And they wondered, could LLMs learn to do the same? Could they be trained to compress their thoughts on the fly?
That's a really cool idea. So they're essentially looking to the human brain for inspiration to solve this AI efficiency problem. I like it. But how do they actually put this into practice?
Well, they realized that the output of LLMs often contains a mix of what they call fluency tokens and reasoning tokens.
Fluency tokens and reasoning tokens, what's the difference?
Fluency tokens are all about generating grammatically correct and coherent language, while reasoning tokens are the ones that carry the logical steps of the thought process.
Ah, I see. So fluency tokens are about style, and reasoning tokens are about substance.
Precisely. And the core idea of LightThinker is to compress those reasoning steps, those important bits of logic, into a much smaller representation without losing the fluency of the final output.
So it's like taking a long, meandering explanation and boiling it down to a few bullet points that capture the essence of the argument.
Exactly. And they do this through a clever combination of modifying the training data, and using a specially designed attention mask.
Okay, I'm definitely intrigued. Let's unpack that. How do they modify the training data?
Well, they essentially teach the model when to compress by inserting special tokens into the data. It's like adding little signposts that say, hey, time to summarize your thoughts here.
So it's like building in prompts that encourage the AI to be more concise.
Exactly. There are two types of special tokens. The first is called the cache token, and it's denoted as C in the paper. This token acts as a container holding the compressed information.
Okay, so it's like a mental sticky note where the AI can jot down its key findings. What about the second type of token?
The second special token is O, and it forces the model to continue its reasoning based only on the compressed information in that cache token.
So it's like saying, all right, you've got your summary, now work with that, and don't get bogged down in all the extra details. I'm starting to see how this could lead to some serious efficiency gains. But you also mentioned an attention mask. How does that fit into all of this?
The attention mask is key. It's like a spotlight that controls which parts of the text the LLM is allowed to pay attention to at any given time.
Okay, so it's like directing the AI's focus, making sure it's looking at the right information at the right time.
Exactly. And in LightThinker, the attention mask is designed to do two things. First, it forces the model to learn how to compress its thoughts into those cache tokens.
So it's like teaching the model the art of summarization itself.
Precisely. And second, it makes sure that the model actually uses those compressed summaries to continue its reasoning, preventing it from getting distracted by the original, more verbose text.
So the attention mask is like a coach, guiding the LLM to be both concise and focused. Pretty clever. But how do you actually measure how well this compression is working? You can't just eyeball it, right?
That's a great question. And the researchers realized that traditional metrics, like just looking at the peak number of tokens used, weren't enough for a dynamic system like LightThinker.
Why not? I'd think that knowing the maximum number of tokens would be pretty informative.
It is, but it doesn't tell the whole story. With dynamic compression, the memory usage can fluctuate throughout the whole process. What's really important is the total amount of information the model has to access.
Ah, I see. So it's not just about the peak, it's about the overall memory footprint throughout the entire thinking process.
Exactly. So they introduced a new metric called dependency.
Dependency. Okay, I'm all ears.
Dependency measures the total amount of information the model needs to access throughout its entire reasoning process. You can visualize it as the area under the context length curve over time. The lower the dependency value, the more effective the compression.
So a lower dependency means the model is relying on less information overall, indicating that the compression is working well.
Exactly. And when they tested LightThinker on the Quinn model, they found some pretty remarkable results.
Okay, let's hear it. How much did LightThinker improve things?
Well, LightThinker reduced peak token usage by a whopping 70% and inference time by 26% compared to the vanilla Quinn model.
Whoa, 70%. That's a massive reduction.
Yeah.
And they didn't sacrifice accuracy for those gains, did they?
Nope, they didn't. All of this came with just a 1% drop in accuracy.
That's incredible. It sounds almost too good to be true. But did they only test it on one specific type of problem?
Oh no, they tested it on 4 different data sets. GSM-8K for math problems, MMLU for general knowledge, GPQA for question answering, and BBH, a benchmark designed to really challenge these reasoning models.
Okay, so they really put it through its paces, and it held up across all those different tasks.
It did. The results were consistent, showing that LightThinker is a robust approach, not just a one-trick pony.
That's really exciting. It suggests this could be a general solution for making LLMs more efficient thinkers.
Exactly. And they even compared LightThinker to some of the existing solutions we talked about, like H2O, which prunes tokens based on importance.
Oh, I'm curious to hear how it stacked up against the competition.
Well, LightThinker consistently struck a better balance between accuracy and efficiency. It significantly outperformed H2O, especially when it came to inference time.
So not only did it reduce the amount of data the model had to handle, but it also made the thinking process faster. What about an LLM? I remember you mentioned that one earlier as being similar to LightThinker.
Yes, ANLM also uses a form of compression, but it's designed a bit differently. And again, LightThinker came out on top with both higher accuracy and faster inference times.
Wow. It sounds like LightThinker is a real game changer. But you mentioned earlier that it actually reduced the total number of tokens generated, not just the peak. How is that even possible? Shouldn't a compression method still generate roughly the same number of tokens overall?
That's what's so fascinating about LightThinker. Most compression methods just try to lower the peak memory usage, but LightThinker actually made the model more concise in its thinking. It generated fewer tokens overall, which is a big part of why it's so much faster.
That's really interesting. It's not just squeezing the data into a smaller space, it's streamlining the entire thought process. Did they find any other interesting patterns in how much compression happened? Did it vary by the task at all?
Yes, they did. It turned out that simpler tasks, like those in the GSM-8K dataset, had higher compression ratios.
Meaning the model could summarize its thoughts more aggressively without losing accuracy?
Exactly. And even for shorter texts, where you wouldn't think compression would matter as much, LightThinker still significantly reduced peak memory usage. They found a 72% reduction for generating 1,000 tokens.
Wow, so even in situations where you might not expect it to make a big difference, it's still having a positive impact. Okay, so LightThinker sounds pretty amazing. It's efficient, accurate, versatile, but there have to be some limitations, right? Nothing's perfect.
Of course, there are always limitations. The researchers themselves point out a few areas for improvement. For example, they only used full parameter fine-tuning to train LightThinker, which can be computationally expensive.
Yeah, fine-tuning those massive language models can take a lot of resources.
Right.
What else did they highlight?
Well, they only use a limited amount of data in their experiments. Using larger data sets might lead to even better performance.
That's pretty typical in machine learning. More data often equals better results. Anything else?
They also found that LightThinker didn't work quite as well with the Llama series models as it did with Qwen. So there's still some work to do in understanding how to adapt it to different model architectures.
Interesting. So there's potential for improvement with more data and fine-tuning. Any other caveats our listeners should be aware of?
One last thing. Even though LightThinker reduces memory usage overall, it can still lead to occasional high memory peaks.
Because the compression happens dynamically.
Exactly. So it's not a magic bullet for all memory issues, but it's definitely a step in the right direction.
I see. So it's still a work in progress, but with really promising results. Now, you mentioned earlier that the paper also included a case study where they break down how LightThinker solves a specific problem step by step.
Yes. It's a great way to really see the compression in action.
All right, well, let's dive into that in part 2. Okay, so let's get into this case study. What kind of problem are we looking at here?
So in this case study, they use LightThinker on a math word problem. It's about a chocolate factory, and they have to figure out how much chocolate the factory produces in the last week of a month.
Okay, a chocolate factory. I'm already intrigued. What kind of information does the model get?
They get the total monthly production and then the production for the first 3 weeks of the month. So LightThinker needs to use that to figure out the production for the last week.
Okay, so it's like a little logic puzzle. How did LightThinker go about solving it?
Well, first, it lays out the problem, summarizes the given information, kind of like how a human would start tackling this.
So it's organizing his thoughts, getting everything in order.
Exactly. And then it breaks the problem down into smaller steps, like calculating the total production for the first 3 weeks based on the numbers they're given. And as it's doing this, it's inserting those special tokens we talked about, the cache tokens and the continue reasoning token.
Oh, right. To mark where the compression should happen.
Exactly. So it's reasoning and compressing its thoughts at the same time.
That's impressive multitasking. And I'm guessing this is where the attention mask comes into play.
You got it. The attention mask makes sure that the model focuses on the compressed content, those key points stored in the cache tokens, when it moves on to the next step. And in this case, it all works out beautifully. LightThinker successfully solves the problem.
So it demonstrates how the model can handle sequential reasoning, breaking the problem down into steps while keeping its memory usage in check.
Very cool. But you also mentioned earlier that the researchers found some examples where LightThinker didn't quite work as planned.
Yeah, that's right. There were some cases where, even though the initial thought process seemed correct, the model ended up stumbling on the final answer.
Oh, interesting. So even with the compression, it's still possible for the model to make mistakes.
Exactly. And it highlights one of the risks with any compression method. If the model misses a crucial piece of information during that summarization step, it can lead to errors down the line. It's like if you're trying to summarize a long story and you accidentally leave out a key plot point, it can change the whole ending.
That's a great analogy. And what's interesting is that the researchers found that these errors often happen when the model was dealing with numerical values.
Oh, so maybe the current compression method isn't quite sensitive enough to those numerical details.
That's what it seems like. It kind of highlights the fact that while compression has a ton of potential, there's still work to do in terms of making it super robust and accurate.
I see. So there's a bit of a trade-off. You gain efficiency, but you potentially risk losing a bit of precision. That makes sense. But overall, the results are still really impressive. So where do you see this research heading in the future? What kind of impact could this have on the world of LLMs?
Well, I think this work is super exciting because it opens up so many possibilities. If we can train LLMs to think leaner without sacrificing accuracy, it could make these powerful AI systems much more accessible.
More accessible? How so?
Imagine being able to run complex language models on less powerful hardware, like your phone, or even tiny embedded devices.
Oh, wow. So we could have incredibly powerful AI assistants available to us all the time.
Exactly. And it could also push the boundaries of what LLMs can achieve. If we can overcome these memory and processing limitations, we might see even more sophisticated reasoning abilities emerge.
It's pretty mind-blowing to think about what we could accomplish if we could really unleash the full potential of these models.
It is, but it also raises some really interesting questions about the nature of intelligence.
Questions like what?
Well, if we're training LLMs to compress information like this, are we making them think more like humans? Are we pushing AI closer to human-level cognitive abilities?
That's a big question. It is fascinating to consider how these techniques might be mirroring what our own brains are doing.
Right. Our brains are incredibly complex, and we're still trying to understand exactly how we summarize, abstract, and learn new information. But techniques like LightThinker give us a really powerful tool to study these processes and maybe even gain new insights into our own minds.
It's like AI is helping us understand ourselves better. That's pretty amazing. But let's bring it back down to earth for a second. For our listeners who are AI researchers and ML engineers, what are the key takeaways from this paper? What should they be paying attention to?
Well, first and foremost, LightThinker offers a really compelling solution to these memory and computational bottlenecks that have been holding back slow-thinking LLMs.
So efficiency gains without compromising performance. That's a huge win for anyone working with these large language models. What else?
The introduction of the dependency metric is also really valuable. It provides a much more nuanced way to measure the effectiveness of these dynamic compression methods.
Right, because it takes into account the entire reasoning process, not just the peak memory usage. What about the case study? Any key takeaways from that?
The case study is a fantastic example of how to analyze what's going on inside these models, which is so important for making them more reliable and interpretable.
Absolutely. We need to understand why they're making the decisions they're making, not just what decisions they're making.
Exactly. And the case study shows how LightThinker can be effective, but it also highlights the potential pitfalls, especially when dealing with those numerical values.
It's a good reminder that no solution is perfect, and there are always trade-offs to consider. Any other nuggets of wisdom from the paper that our listeners should keep in mind?
Well, their analysis of the compression ratios across different tasks is really insightful. It shows that the optimal level of compression really depends on the complexity of the problem.
So you need to adjust your compression strategy based on what you're asking the model to do. Makes sense. And their discussion of the limitations of LightThinker, especially with those numerical values, really highlights some important areas for future research.
Definitely. There's still so much to explore and improve upon. This paper lays a great foundation, and I think it's going to inspire a lot of really interesting new research in this area.
I agree. Well, it sounds like this paper is a must-read for anyone working with large language models, especially for those more complex reasoning tasks where efficiency is so critical. We'll be sure to include a link to LightThinker, Thinking Step-by-Step Compression, in the show notes so you can check it out.
Yeah, definitely give it a read. And if you're working on LLM inference acceleration or anything related to making AI more efficient, this paper is full of really valuable insights.
All right, great. Well, that wraps up our deep dive into efficient AI with LightThinker.
Until next time.
It really is amazing to think about just how far LLMs have come and how much potential they still have. But before we wrap things up, I wanted to circle back to something we touched on earlier. The idea that, LightThinker might be pushing AI closer to that human level of cognitive ability. What are your thoughts on that?
It's a fascinating question for sure. And one that, a lot of researchers are really grappling with right now. On the one hand, it's pretty clear that LightThinker is inspired by how humans think.
Right. Like compressing information, summarizing the key points, getting rid of all that extra detail. These are things our brains do really well.
Exactly. And it's pretty remarkable that we're seeing those same principles being applied to AI now.
It really does feel like we're blurring the lines between human and artificial intelligence a bit, doesn't it?
It does. But it's important to remember that we still have a very limited understanding of how human cognition actually works.
No, we don't have the whole picture, not
That's-
even close.
Exactly. So while LightThinker might be mimicking some aspects of human thought, it's probably not a perfect replica, you know?
Right. It's more like we're taking inspiration from the brain, seeing what works, and then applying those principles to AI.
Exactly. And in doing so, we're not just developing better AI, we're also gaining new insights into our own minds.
It's like AI is helping us understand ourselves better, which is pretty amazing when you think about it.
It really is. And this paper is a great example of that. It's a technically impressive piece of work, but it also raises these really profound questions about, what is thought? And what is the future of AI?
I completely agree. Well, I think we've covered a lot of ground today. Any final words of wisdom for our listeners before we sign off?
If you're interested in making LLMs more efficient, I would definitely recommend diving deeper into the paper. Pay close attention to how they design that attention mask and how they evaluated the performance using that dependency metric.
Great advice. We'll include a link to the paper, LightThinker, Thinking Step-by-Step Compression, in the show notes.
Yeah, and if you're working on LLM inference acceleration or really any research that involves making AI more efficient, this paper is definitely worth a read. It's got some valuable insights into the challenges and potential solutions in this area.
Okay, so for all you AI enthusiasts out there, add this paper to your reading list. And as you continue exploring the world of artificial intelligence, I'll leave you with this thought. If we can train LLMs to think leaner, what other cognitive processes can we optimize? Could this lead to AI that learns even more like humans, abstracting away from raw data and forming those more generalized representations? Keep those algorithms humming, everyone.
And keep those minds curious.
Thanks for joining us on AI Paper Podcasts.